All right, Dr. Marshall, we're going to go ahead and get started.
Okay, thank you.
All right, good afternoon, everyone, and welcome to today's Biomes. I'm glad to see everyone is here and enjoying their pizza. I'll introduce our speaker for today. We have a great speaker. I'm really excited to hear about his work. So our speaker for today is Dr. Marshall Shephard. He is the Georgia Athletic Association Distinguished Professor of Geography and Atmospheric Sciences at the University of Georgia and Director of its Atmospheric Sciences Program. In 2023, Shephard was selected as Associate Dean for Research, Scholarship, and Partnerships at the Franklin College of Arts and Sciences at UGA. In 2022, he was selected SEC Professor of the Year. In 2021, Dr. Shephard was elected to the National Academy of Sciences, National Academy of Engineering, and the American Academy of Arts and Sciences. The only member of the University of Georgia faculty to ever achieve this trifecta, and likely one of the few scholars in the nation to do so. Dr. Shephard was also the 2013 president of the American Meteorological Society. Prior to academia, he spent 12 years as a scientist at NASA Goddard Space Flight Center and was deputy project scientist of the Global Precipitation Measurement Mission. Dr. Shephard is the host of the Weather Channel's Weather Geeks podcast, which I love, and a senior contributor to Forbes magazine. In 2004, he was honored by President Bush at the White House with the Presidential Early Career Award for Scientists and Engineers. He has also received the Captain Planet Foundation Protector of the Earth Award, the 2019 AGU Climate Communication Prize, the 2020 Manny L. Baumick Award for Public Engagement with Science, and 2018 AMS Helmut Landsberg Award, to name a few. He received his BS, MS, and PhD from Florida State University. He has 3 TED Talks on climate science and communication that collectively exceed 2 million views. He is routinely asked to brief Congress, the White House, and other agencies on weather, climate science related topics, and recently moderated a discussion with Vice President Kamala Harris on climate related topics. He routinely appears on major media outlets like CNN, CBS, Face the Nation, PBS Nova, and the Today Show. Dr. Shephard has almost 100 peer-reviewed publications and is responsible for over $30 million in extramural funding since arriving at the University of Georgia. He serves as one of President's Moorhead's appointees to the UGA Athletic Association Board. So help me welcome Dr. Marshall Shephard.
Thank you. Thank you so much for that introduction. I'm going to try to go ahead and share my screen and we'll get going here. So can you see my screen okay? I can't see anything to give you a thumbs up or see if you can. So I'm assuming, okay, I'm good.
No, we don't see it.
You don't see it?
No.
Oh, okay. Interesting. Okay, let's try that again.
Good to go.
All right, great. So thank you. Well, first of all, I want to thank you all for having me. I am actually just taking on a new role as an associate dean here at the University of Georgia. So I'm up in my office in that new role. I haven't even gotten much of my furniture and everything moved in yet. So it may seem a little sparse and maybe even echoey as I'm talking to you. I apologize for that, but I needed to be up here for some meetings later today. So what I thought I would do when I was invited to do this talk, I was given the option to talk about my research or anything else, I guess, that I wanted to talk to in this space. So what I thought I would do is actually present a holistic talk that integrates aspects of my research into the talk. And so it'll be a broad talk on perspectives on climate change, urbanization, risk, and vulnerability. but I think that you will see several threads of my research emerge in talk as I give the talk. And so, again, thank you for the opportunity. I can see you all in the room there. I'm good friends and colleagues with Professor Karen Sito, who I don't know if she's in the room, but if you're not taking classes from her or interacting with her, she's one of the top scholars in the world. And many of her research topics intersect with mine. In fact, we've published a paper together, what I think is a very important paper on urban climate related issues. So if you are on Twitter, or what they call X these days, feel free to give me a follow. I'm at Dr. Shephard 2013. And I often share that before I start to give a talk because I want people to engage. I want them to share broadly what I'm saying or talking about, because we have to get our science out of the ivory tower. I'm adamant about that. And in my citation for membership, when I was elected to the National Academies, talks about my work in urban hydrometeorological processes, but it also said it's also moving science out of the ivory tower in effective ways. And that's very important to me. So give me a follow on Twitter. I'm also on TikTok at Dr. Shephard Knows, and you can find me in other spaces as well. So with that, let's launch right in. So in 1973, design theorists Rittel and Weber introduced this concept of wicked problems. And their intent was to draw attention to the complexities and the challenges associated with societal problems, particularly as it related to policy. But over time, this concept of wicked problems or wicked challenges has emerged to consume many things that I think about as a meteorologist or as a climate scientist or simply as a human being living on the only planet that is known to support life at this moment. And so when we think about this intersection, it came to mind because I have a 16-year-old son who recently got his driver's license. And as I looked at this particular intersection, I said, that would be a wicked challenge for him as a new driver. But what we actually know is most of the challenges that we face today, whether it's COVID-19, race issues, climate change, are wicked challenges at the intersection of science and society. So the context and framing of my remarks today and my discussion will center around climate and weather, but at various scales. So what I'm showing you right now is the land ocean temperature percentiles from January through September of this year. And what clearly should jump out at you is not a surprise. The planet is warm and is warming. And in fact, where you see those deep reds, those are significant and record warming across the planet. That's been the narrative, that's been the headline for the last several years and decades. Now, I am fully convinced that at the end of this year, we will have lived through the warmest year on record. And again, that's due to climate change, the fact that we're in a very strong or strengthening El Nino pattern, and also summer variability that we would expect in a naturally varying climate as well. Here's another way to look at just how warm we've been. This black line represents 2023, and these red and blue lines represent previous decades through the last 100 years or so. 2023 is shattering our warmest years on record. I mean, things that were record warm years so far, we're shattering it, particularly since the latter part of the spring. September was record warm. In fact, if you look at September, it was as hot globally as what we would expect in the warmest July. Let that marinate for a second. So that gives you a sense of just how warm the year 2023 has been, and particularly the recent months. Here's another way to look at it if you want a different perspective. The bottom line is 2016, which was our previous warmest year on record, and also an El Nino year, by the way. 2023 is going to shatter it. I mean, it's like Usain Bolt, track star, breaking his 100-meter dash record by 3 seconds. It's just unheard of. It's usually by tenths of a second. That's how much we're pacing ahead of some of the warmest record years we've seen. And, I set that context, but what I really focus on in my work is risk associated with extreme weather and climate disasters. And so you can look at the number of events last year in 2022 that exceeded the $1 billion threshold in terms of cost. And in many cases, it's exceeded it significantly. For example, Hurricane Ian in Florida, likely going to be a $150 to $175 billion disaster. And so this changing climate system that I've sort of talked about is changing aspects of our weather and climate in many ways. So we know that climate is changing, and these are the reasons why. I don't necessarily need to sort of spend too much time there, but I will just remind you that we have a greenhouse effect. You see it here on the left. We couldn't survive every night if we did not. So we survive every night because of this greenhouse effect and the greenhouse gases in our atmosphere. It provides a habitable temperature range for us as human beings. Otherwise, we'd freeze to death. But since the Industrial Revolution, we have sort of outpaced the sort of equilibrium balance of this greenhouse effect. And so now our lower atmosphere is warming, and that's why we are seeing human-enhanced greenhouse effects and climate warming. So the climate will be changing. Again, in this particular audience, I probably don't need to make this point, but one thing that's subtle in there is that I said I think that we have to move beyond the narratives of talking about things in the future tense. Well, this is what's going to happen, or this is what's going to happen in 2050, or this is what we expect. It's happening. And so our scholarship needs to be framed or recalibrated from a current event standpoint rather than a future. And of course, future is relevant. But again, oftentimes when scholars talk about climate change, they talk about it from the perspective of what's going to happen. So with that, now let me sort of come down scale. Okay. And I want to talk about how I frame much of my research these days. I often think about risk from a climate and extreme weather perspective. And so, borrowing from the World Risk Report and Brooks 2003, I've always liked this framing or definition of risk. So risk is a function of hazard, exposure, vulnerability, and resilience. Now, let's break down these terms. The hazard is the heat wave. It is the hurricane or the flood or the drought or the wildfire. The exposure is who is impacted by and experiencing those hazards, whether it's people, infrastructure, or assets. Vulnerability is sort of wrapping up this notion of you're exposed to the hazard, who has the greatest sensitivity to that exposure. And then resilience is not the inverse of vulnerability simply, but I like to think of resiliency as this ability to bounce back from the exposure to the hazard. So it's a measure of adaptive capacity, if you will. At least that's how I'm using it in this context. And so much of my research on heat, flooding, storms tries to think about things from this perspective of this little risk equation. So think about that carefully as I move forward in my discussion today. So here's the state of Georgia. I live in the state of Georgia. In fact, if you want to have an idea where I'm located at this very moment, it is right there. That's Athens, Georgia. That's where the University of Georgia is located. This is Atlanta, obviously a much larger, sprawling urban area. And I live somewhere in that sprawl. I live in Gwinnett County, which is a suburb of Atlanta. And so I actually make a 35-minute commute each day from Gwinnett County over to Athens. Now, much of those global and large-scale weather and climate events or hazards that I talk about scale to states or scale to cities. And so, for example, this is a look at, and I'll back out for a second, the urban heat island of Augusta, Georgia. Augusta is a mid-sized city in the state of Georgia, And this is some work we've been doing recently as a part of a DoD project, Department of Defense, Department of Energy and Savannah River National Labs effort to not only understand the urban heat island of Augusta, but also to understand whether this urban heat island is producing what we call hydrological urban heat islands. This idea that when it rains, it's falling on hot surfaces and getting into the streams and rivers like the Savannah River, which is bisecting the city, or other streams and ecosystems. And so the urban heat island is nothing new. I mean, Karen Cito and many other folks and myself have talked about the urban heat island for many, many years. But recently, we've been trying to understand the ways that the urban heat island and the urban environment in generally affects aspects of the hydrometeorological cycle, meaning precipitation, surface runoff, and so forth. And so this is one example of how we utilize, in this case, land surface temperature from satellites, let's say Landsat 8, to map the urban heat island. But I could take this research from just this map in many directions. I could look at things like how water is being heated as it runs off these surfaces, but I can also, and we're doing this, look at who's living in the hottest part of these urban heat islands from a socio-demographic standpoint, and I'll show you some examples of that a little bit later for Atlanta. Well, here is another aspect of that analysis. This is looking at 20 years roughly of rainfall in the summertime aggregated over Atlanta. It's average daily rainfall over a 20-year period. And what we find is something that we have found in many studies that we've published, and that's that over and climatologically downwind of cities, there tends to be an anomaly in increased or enhanced rainfall. So we've done this for much larger cities like Houston and Atlanta and so forth. We decided to look at it for a mid-sized city too. And lo and behold, in our analysis, and again, this is using radar and rain gauge data, we find that over and downwind, this is climate, we look at a climatological downwind based on an assessment of the wind rows and wind regimes of the city. So this is climatologically the downwind part of Augusta, and we see a tendency for a more enhanced rainfall in that region. So this leads me to sort of some work that we published in 2015 in the state of Georgia. We published what we think was the first climate vulnerability index for the state. And so what we did is we looked at the previous 30 to 40 years, several decades, at the heat waves, floods, and drought conditions in counties over the last several decades. And what you see is that the state of Georgia, oh, by the way, the vulnerability index also includes who lives in the counties, not just the geophysical hazard, but measures of social vulnerability as well in terms of race, poverty, infrastructure, and access to healthcare, and so forth. So we matched that together into this climate vulnerability index, and you can find the paper here, KC, Shephard, and Johnson 2015. So you can see a few things. One, the state of Georgia has become more climate vulnerable over the last 30 to 40 years. You can clearly see that it went from a yellowish to an orangish red. But then if you look more carefully, you see that our urban counties, Atlanta area, Savannah area, Macon, Columbus, Augusta, are more climate vulnerable than surrounding rural areas. We do have some highly vulnerable counties in the South. This is our agricultural region of the state. Each of these counties are climate vulnerable for different reasons. In Atlanta, it's mostly due to increased elevated heat and flooding on those vulnerable populations. In the coastal communities, it's primarily flooding. And in the interior, it's exposure to increased drought. And that leads to variability in terms of when people can go to work, because this part of Georgia is very dependent on agricultural productivity. So let's take a look at this little graphic that NASA developed. I spent 12 years of my career at NASA before I was at the University of Georgia. And if you're someone like me that does urban related research, this is a very disturbing distribution trend. We started this graphic in 1960s, and it will go up through about 2020 or so. Actually, maybe 2022 if I put the most recent. No, I stopped it at 2020. One of the things that you should take away from this is that the normal distribution has shifted, if you will, in terms of the median. So if you look, things that were sort of out here on the warm end of the spectrum in the 1960s are now normal events, right? So extreme events from the 60s are now normal events in 2020 and beyond. And the extreme events of today are something else. They're a different beast, if you will. But here comes the thing that worries me when I think about urban heat and urban risk. Look at the shift in the low temperatures, the nighttime temperatures, the temperatures overnight are shifting to the warmer regime as well. And that is of concern because that's where we start to see health-related outcomes and health-related vulnerability. So, for example, this summer, parts of Phoenix, Arizona were elevated in temperature. The headlines were talking about 115, 118 degree temperatures for consecutive days. And that is of concern. But what worried me more was the fact that when I looked at those cities, their temperatures at midnight were still around 90 degrees. Now, that's a problem. So let's take a look at why that's a problem. I'll stay here. The heat wave in the Pacific Northwest in the 2021 timeframe was an anomalous event. Hundreds of people died. Many people in those homes did not have air conditioning. If you go and look at the heat conditions in Europe this summer, 85% of the homes don't have air conditioning in places like London, but they had 104-degree temperatures there. So the nighttime temperatures being elevated increases or enhances risk for heat and death, heat-related illness and death, and that's what we are starting to see. Now, while I'm focusing on heat, much of my work over time is focused on rainfall, hydrometeorological processes, hydrometeorological water aspects of weather systems. That's where my research mostly lies. And so here's a look at how precipitation has changed or is changing or distributed around the United States. And you can see some areas are wetter than other areas, right? Seasonal changes are at play, natural variability is at play. But what we also know is that places that are wetter are becoming wetter and places that tend to be drier are becoming more dry. But the extremes are what concern me. This is from the Global Change NCA, the National Climate Assessment Report. What we know is that the increases in the high-end rain events are evident in almost every region of the country. In other words, in the Southeast, the top 1% rain events, that means when you see a really heavy rainstorm in terms of intensity, it's more intense than it was in 1958. So you're up here in this region, you're in New Haven, Connecticut, I believe, or somewhere close to there. In this region, the rainstorms, the top 1% events are 55% greater than they were, a half a century ago. Why that's important is that many of our stormwater management, much of our stormwater design was designed under the assumptions of stationarity, which is that the rainstorms of 1958 will look like the rainstorms of 2023. They don't. They're much more intense now, as our own data has shown. So we're seeing older cities with infrastructure that has not been updated in terms of stormwater removal, being overwhelmed. And not just older cities, cities generally, because much of our stormwater hydrological engineering was designed under that assumption, that false assumption of stationarity. Now, there's a basic physics principle. It's called the Clausius-Clapeyron relationship. Clausius-Clapeyron relationship says that as our climate system warms, our atmosphere warms, it has the capacity to accept more water vapor. So If you look to the left, this is sort of our previous scenario. To the right, we've got more evaporation, so there's more water vapor available to the atmosphere, available to rainstorms, hurricanes, and even snowstorms. So when you hear these nor'easters coming up into your region, there's certain studies that suggested that they may have more intense snow rates. And that's counterintuitive to people because climate warming is leading to more water vapor availability to the atmosphere, which in turn means more water vapor availability to storms, whether they're snowstorms, rainstorms, or hurricanes. So this is a look at a police officer here in Atlanta just a few weeks ago. We had tremendous flooding in the city. Dorms were flooding in some of the universities in Atlanta. It's just a manifestation of what I just talked about. And so this is some work we've done sort of pulling together flash flood warnings over a 20-year period in Georgia. And what you see is the most flash flood warnings issued by the National Weather Service tend to be in our mountainous regions when that's expected, but also in our urban environments. And that's important to understand because flash flooding is not just a function of what falls from the sky. It's also a function of the urban imperviousness, because remember, that heavy rain that's falling to the surface, if there's impervious surfaces there, it doesn't infiltrate into the soil like we would expect from a natural water cycle. It doesn't infiltrate. In fact, it runs off rapidly into streams, rivers, and so forth, and they rise, and that exacerbates or amplifies the flooding. So we have a positive feedback, if you will. So that's what we see. In fact, this is, again, some recent research from one of my students, Lindsay Nixon, from our master's thesis. And what we were interested in understanding is there is a metric that we use called flashiness. Again, it's a sort of a metric of how flashy streams are. You know, when they receive rainfall, how flashy are they in terms of their tendency to produce flash floods? And what we found is a strong correlation between Georgia's flashiest streams being in urban environments as opposed to some of the rural environments. This is a paper that we hope to publish very soon. So we have a new normal weather and climate. We see worrisome trends. This is the roadway connecting Savannah, Georgia to the coast. We know that there are a reduction in things like work hours and so forth because of the heat loads. This leads me to some more recent work we've been doing in Atlanta. Urban heat amplifies climate change and heat wave impacts. So when I talk about heat, I often talk about the triple whammy effect. We've got broader global climate change, which is warming the planet. And that is in turn increasing the intensity and frequency of heat waves like we saw in Portland or we saw in Europe. And then we have the urban heat island. And I showed you the Augusta urban heat island. Now here is the Atlanta urban heat island. Again, taken from satellite data. In this case, MODIS, which is an instrument aboard the Terra and Aqua spacecraft, has a little more coarse resolution than that Landsat data set that I showed you for Augusta earlier. But you see the urban heat island. But what we found is when we decompose the urban heat island by where people live and their race, we see that communities of color are disproportionately living in the hottest parts of Atlanta's urban heat island. So I've called these in a recent book chapter racialized urban heat islands. And so the chapter should be published soon, hopefully, but much of that sort of spatial relationship can be traced back to some historical redlining practices that happened a century ago. You know, banks, mortgage lenders, and so forth would literally draw red lines on maps of places they weren't going to fund or give loans to. Over time, those parts of these cities that were redlined became more industrialized, less residential, less vegetation, and again, less valuable from a land standpoint too. So communities of color and lower income communities have now moved into that less desirable parts of the city, but they're hotter because they're less vegetated and they're more industrialized. And so the National Climate Assessment identifies these particular communities as the ones that, again, when we talk about that risk scale, that risk equation earlier, These are the folks that have the greatest sensitivity and the least amount of adaptive capacity to these extreme events. So, it's depressing, frankly, if you just sit here and talk about these things and don't think about solutions. So I have been working with Georgia Tech, Arizona State, North Carolina A&T on an initiative to try to engineer cities for thermal justice. We see that there are thermal injustices in terms of distribution. Working with some mechanical engineers and other colleagues, we've thought about some fundamentally sort of novel and innovative, radical approaches to reimagine how we engineer cities to repurpose, redistribute, or disperse heat in ways that are well beyond planting trees or painting pavements white. Those are sort of low-hanging fruit, and they definitely can have some short-term mitigative strategy. But we're talking about fundamental reimagining how we engineer cities with thermal justice in mind. So this is me sitting before the House Science Committee in Congress a few years ago, and I warned them at that time that the extremes are becoming more extreme. We know that there are naturally varying climate conditions. Trust me, I have people who are maybe climate contrarian or skeptics say, well, climate changes all the time, or climate changes naturally. Of course it does, but we now have a human steroid on top of that naturally varying climate. I often use the analogy that grass grows naturally, but when we fertilize our lawns, it grows differently. So we have to move away from this notion that it's an exclusive either or. It's not. There is naturally varying climate, and there's an anthropogenic signature on top of it, just like grass grows naturally, and when we fertilize it, it grows differently. So I spend a lot of time there because that narrative is pervasive. So I was the co-author on a report from the National Academies about 6 years ago, where we looked at this burgeoning area of climate science called attribution. What can we say about current weather events and whether they have the DNA of climate change in them? And so what we found is that these events on this part of the scale, as of 2016, are the ones that have the most attributable signals to climate change in them today. Extreme heat, the lack of or the reduction in extreme cold events, drought, extreme rainfall. Tropical cyclones or hurricanes fall in the middle because we just don't have a long enough data record, and we can't reproduce hurricanes as well as some of these other things in the climate models. Severe convective storms, things like tornadoes. We think that there are probably links, but the literature is not conclusive yet. So as of 2016, severe convective storms, tornadic storms fell down here. Recent National Academies effort that I was involved with, I'm on the board of Atmospheric Sciences and Climate, the BASC at the academies, and we had a review or sort of a revisiting of this study, and I think we probably can move both wildfires and severe convective storms up some since 2016 based on some of the recent literature. And so here we go. One of the things that really is concerning me as a climate scientist right now, and I do work on hurricanes, the rapid intensification of hurricanes. We're seeing storms. Now, what is rapid intensification? That's when a hurricane gains 35 miles per hour of wind speed in less than a day. Now, if you watch Hurricane Otis recently, it made landfall near Acapulco, Mexico, significant storm. It went from a tropical storm to a Cat 5 in about 13 hours. And again, I think it gained 70 to 80 miles per hour wind. It's just unheard of. But what's concerning is that we're seeing rapid intensification because of, these storms have quite a bit of high octane fuel because of the warming of the oceans. Remember, most of the climate warming is in the oceans, in the water, not the atmosphere. So storms like Otis have quite the potential energy source to tap into. So this is Hurricane Ian. We've done research. I published some research a few years ago on the rainfall production in tropical cyclones. And the point of that paper was to establish a baseline for how much rainfall is being produced by tropical storms versus Cat 1s versus Cat 2s, Cat 3s, and Cat 4s. And ultimately, we'll spin up some new research here soon on whether hurricanes are becoming wetter. Are they producing more rainfall in this climate-enriched environment? The other work that I do on hurricanes is, if you've heard of this concept called the brown ocean effect. We've studied the brown ocean effect. We actually came up with the term in a few papers back in 2013, and we've continued to do this work, is when hurricanes move inland, they're supposed to weaken because they lose their water or energy source. But if there had been previous rainfall on the land surface, or if it moves over a swamp or a marshland, we found that these hurricanes can maintain their intensity or even intensify. And so, hurricanes aren't intelligent beings. They don't know that they're not over the ocean if they're over a very wet soil mass. And so that's this concept of the brown ocean effect. So to sort of summarize, I mentioned the 2021 Pacific heat wave. A new attribution study, it's about a year old now, found that Pacific Northwest heat wave was 150 times more likely due to global warming. In other words, theoretically a 1 in 150,000 year event. So clearly the signature of climate change was in this heat wave. There might have been a heat wave 100 years ago at that same exact time, but it would not have been that intense. And you can see the sort of trends in June temperatures compared to the 20th century average down here. So I want to wrap up sort of this talk in terms of the broad big picture, how some of my work at scale fits in, and where we need to go forward. So climate is changing and extreme weather events are responding. Hope and let's wait and see are no longer viable risk mitigation or resiliency strategies. We can make some headway at the broad sort of international and global scale with things like the Paris Agreement, but we can also do some things at the state and local level. We've done something here that I've been a PI on called Drawdown Georgia. We took the project Drawdown philosophy and did a very rigorous quantitative study with some funding from the Ray C. Anderson Foundation to look at what mitigation strategies will have the most effect on reducing CO2 emissions in the state of Georgia. We found that there are 20 solutions that make sense to focus on here in this state. That 20 solutions may look a little different for Connecticut, for example. And climate resilience is going to require a mix of traditional engineering, but also the types of things we propose with our thermal justice project, and nature-based engineering, or engineering with nature solutions, which is an area that we've been kind of getting into here at the University of Georgia. I'm a part of an institute here called the Institute for Resilient Infrastructure Systems, or IRIS. And so we've been working with the Army Corps of Engineers on nature-based solutions to mitigate and adapt to hurricanes, urban heat, and urban flooding. So this is a graphical view of my risk framework that I presented to you. This is a paper that we published in 2021 showing you what we believe to be the most at-risk climate counties by the year 2040 in the United States. Now, when you look at this, you might say, oh, wow, most of the country is yellow. We're not at climate risk. Not so fast, my friends. This is a deliberately right-skewed scale in order to really amplify the most at-risk counties to climate. So in other words, all of the yellow that you see, those counties certainly exhibit climate risk. But the counties that you see in blue, purple, and brownish orange are the ones that are flashing, hey, we're all vulnerable from a climate and a social vulnerability standpoint. So you can see many of our coastal counties, many of our urbanized counties, and we can come up here into the Northeast as well, see Southwest and so forth. So here in the state of Georgia, most people think global warming is happening. This is some work from the Yale Climate Change Communication Group. My good friend Tony Laceros and the folks over there have been doing quite a bit of work. They sample the U.S. population every year in their 6 America study. And so it's interesting to see that even in a state where you might think that people will have some thoughts, the vast majority of people do think climate change is happening. And so I think we have to take advantage of what I believe to be a shift in the narrative. There are, as the Yale Climate Group says, a few percent of the population that's dismissive. They're the ones that tend to be the loudest in Twitter, or that uncle at your Thanksgiving dinner that shows you the latest YouTube theory on something. But for the most part, people are a place where we've moved beyond those kind of discussions. And now we've got to move to beyond climate delayism to actually taking action. And I think we're in that phase now. So what I try to do is contextualize some of my individual research within a broader climate risk and vulnerability framework. So thank you for listening.
All right, we have time for a few questions.
Hi, Dr. Shephard. Thank you for your presentation.
Thank you.
My name is Phoebe. I am a joint degree student between the School of the Environment and the School of Public Health. So I'm really interested in risk communication. And I'm also a student employee of the Yale program on climate change communication. So that was exciting to see their data in your slides. But I mainly had a question related to your slides on the vulnerability index for Georgia and the climate risk map. And
Yes.
I think you were saying those are really like aggregate values of different hazards. And those different hazards have very different like management and adaptations.
And hazards and socioeconomic indicators as well.
Yes, of course. I was just curious, like from a communication standpoint, like do you find that aggregating all of that is like useful and easy to understand for the public, or like is it more helpful to break those out by hazard type and vulnerability type?
I think it depends. If you read, thank you for the question. I have an article I wrote called 9 Tips for Communicating Science to Non-Scientists. And in that, the first sort of recommendation, and that's in Forbes, I am a senior contributor to Forbes. And in that, I talk about knowing your audience. So I think there are cases where the aggregate values are at work. So I would probably show the aggregate values to Congress or to certain audiences. But I think if I were going into a community that was worried about flooding in Southwest Atlanta or Proctor Creek, I probably would break things out in more sort of in higher sort of resolution or precision to show them specific hazards. So I think a real lesson for risk communication for all of you is the answers can be both. It just depends on your audience.
Hi there. Can you talk more about the thermal justice project you're working on? Like
Sure.
what kind of solutions beyond the low-hanging fruit are you looking to see is viable?
Well, if I tell you, I'd have to lock you in my basement for 100 years because it's still proprietary. No, the reality is we are still trying to get this funded. So some of the technologies are still, somewhat proprietary. But I'll give you one example. So in this laptop that I'm using to speak to you right now with, there's a really interesting sort of engineering technique within the laptop to cool the laptop transistor systems that involves a thermal tube. How this project emerged is a mechanical engineering professor at Georgia Tech named Yogendra Joshi said, look, I have been spending a good portion of my career helping Google and Apple and all these high-tech firms get rid of excess heat from their server farms and their computer data centers and so forth. What if we could do some of these same techniques on the scale of a city? And so that's kind of how it emerged. We wrote a proposal and got some planning grant funding from the National Science Foundation. So, I mean, it involves things like thermal tubes, microgrids, and various other engineering concepts that are around, and some of them would need to be engineered or developed. But again, it's really reimaginative technology that would not just mitigate the heat, but perhaps in some cases repurpose it or redistribute it for use.
Hi, thank you for your talk. I think I probably had a very similar question, but here in New Haven, we are focused on planting trees. I don't know how big a heat island we have. We're a small.
I'm sure you do.
Yeah.
I'm sure you have one in summer at least.
So my question was, and you may have touched it, but maybe you could also be specific for a smaller city. What can we do to sort of reverse the heat island effect and therefore the effect
Sure.
on the health of individuals in New Haven? Thank you.
Yeah, absolutely. So I'm trying to pull up as I'm going to quickly share my screen again. if I can.
We have about 120,000, I think, is our population in our city.
Yeah, no, I think there's actually been some work in your area. I found something on your website, actually. This is a new algorithm. Can you see that?
Yes.
Are you seeing what I see? Okay, so it looks like this is some work that I found. I don't know if this is Karen's work or some folks that, but it's someone at Yale that's sort of mapping out the ability to look at the heat islands in the Northeast and using probably some new AI techniques. So clearly you do experience or have a heat island there. Yeah, a heat island happens because of 3 to 4 factors. One is the thermal properties of things that we use in cities retain heat and re-emit it. And so the atmospheric or air temperature heat island tends to peak at night because it absorbs that heat all day and re-emits it at night. The skin temperature or surface heat island, and by the way, they're different types. You often hear people talk about the heat island, and I've done it today, but if you read some of my papers, there are actually several types of heat islands. There's a skin or surface temperature heat island. There's an air or canopy layer heat island. There's a boundary layer heat island. I mentioned hydrological heat islands earlier, and I also mentioned racial or racialized heat islands. So all of those are there, and the heat island at its core is caused by the sort of heat absorbing and emitting surfaces, the lack of vegetation, anthropogenic waste heat term, and this notion of buses riding by with heat engines and so forth. In fact, a really interesting study that I sort of summarized in a GRL paper, Geophysical Research Letters paper a couple of years ago, showed that during COVID lockdown, Chinese cities' urban heat islands were reduced. Now, that was really interesting because, what it turns out is that because there were less cars and buses and trucks on the roadway, that anthropogenic waste heat term was reduced. And so the conduction of that heat onto road surfaces was less. It was actually somewhat counterintuitive. It was a really fascinating study. So absolutely planting trees and even doing some albedo modification and greenscaping and these types of things can certainly locally reduce heat. I think there's a methodology, and I think College of Environment and Design type folks can tell you the strategies, because there needs to be a strategy to how they're planted and how they're distributed, just in terms of don't go plant trees. There's actually sort of a methodology, and I'm sure you all are aware of it. I volunteer for an organization, and I haven't in recent years, but in the past, for an organization here in Atlanta called Trees Atlanta, which strategically has been trying to green the city of Atlanta more for some of these very reasons. One of the big challenges we have with measuring heat islands anywhere, whether it's Atlanta or New Haven, is that you often don't have good observations in the heat island. Most of our observations, at least at meteorological, or for good reasons, are out in suburbs or rural areas due to the challenges of urban canyons and sort of urban infrastructure and urban morphology. It's hard to place good meteorological observations in cities. So one of the things you've been seeing in recent years is sort of crowdsource or sort of crowd-involved heat island campaigns. We have one here in Atlanta where people are wearing sensors or riding around on bicycles, trying to get detailed, fine resolution measurements of the heat island. So, but one other thing, I guess the short answer to my long-winded answer is that yes, trees and albedo modification certainly work, but one of the things that we may need to take a look at again is just how much of a contribution that waste heat term from buses and HVAC systems is contributing, because I think it might be more than we had initially thought.
Thanks for speaking with us today, Dr. Shephard. I'm wondering if you are looking into any solutions that leverage increased precipitation that you mentioned was happening in urban areas to combat the urban heat island effect through cooling, evaporative cooling, et cetera, in buildings and such?
Well, most of what we find about enhanced rainfall in cities is typically downwind, but one of the ways that I've proposed that we can leverage that is if we know that we have these sort of downwind regions of an amplified or enhanced rainfall, those might be places where we strategically place agricultural fields or water collection reservoirs for drinking supply. So here in Georgia, much of our water is from surface, at least in North Georgia, is from surface reservoirs. And so if we know that they're preferred regions of rainfall in the summertime because of these urban effects, let's leverage that to collect that water for use. So that's really mostly how I've thought about that particular adaptation.
Right. Hello, Dr. Shepherd. So in your presentation, you briefly discussed climate skepticism, and then you've talked about you've done a few hearings in Congress and
Sure.
at the White House. So how have you dealt with any climate skepticism on that level, and how have you kind of handled it?
Honestly, not really. That's why I think there's a misconception that there's more. You hear a lot about it, but and the last time I briefed Congress in 2019, I think both sides of the aisle were very interested in hearing what we had to say, and I thought all of the questions were very reasonable because at the end of the day, these folks sort of understand that their constituents who are being impacted by floods and hurricanes and heat waves and droughts. So they were really more in. Now I don't think you hear as much of the no, it's not happening, or you guys are crazy, or you're trying to get grant money and all that kind of stuff that we used to hear. Now, you will hear people maybe not call it climate change or global warming, but if you talk to them or talk to their staffers, they're concerned about the heat wave or the drought or the flood, and they just won't. And again, one of my messages to scholarly communities like yours and mine is that you have to be okay with that. You can't expect people to talk about it and say the words like you want them to say it, or you, oh my gosh, you got to say it. You don't. You have to meet them where they are in terms of the value system and work to get to a solution. I think many academics and I'm, one of them, tend to be very idealistic and for good reason, and also concerned and alarmed for good reason. But oftentimes you also have to be pragmatic. And that's one of the things that I think that, as scholars, we have to be pragmatic about our engagement with policymakers and decision makers and so forth. So, they might not say the words, but you can hear, if you listen carefully, some of the things they're saying, that they get it and they understand, or you can see that they're moving their state towards more solar power or EV charging stations and so forth. So that's mainly been my experience more in recent times. Now, there is climate delayism. I was at a White House conference call last year on this because there is a debate about the cost and how much we allocated budgets for doing things. So that's kind of where the debate has moved in national policy circles, at least.
Okay, so we're in the Q&A there. Let's give Dr. Shepherd a hand, and thank you for joining us.
Thank you.